The shared memory and message queue methods were used for inter-process communication in the same operating system. That means both processes were on the same computer system. Uh, it is also possible to have communications between processes that are not necessarily on the same system. So we talk about what we call the client-server systems, where you have one or more clients communicating with a server process, which is typically on another machine across the system. But of course, you can have the source and the destination computers to be the same, so you can use this approach also for communications on the same computer system. But as I said, in general, when we say client-server systems, we typically mean the server residing on a different computer system. Yet, it deserves a discussion also here. Of course, this is a very broad concept, but we will just have a brief look at these because, as I said, it's a very closely related concept. So we will talk about three basic methods. The first one is sockets, creating sockets and communicating over the sockets. The second one is making use of remote procedure calls, RPC. And the last one is making use of pipes, ordinary pipes or named pipes, as we will see. So let's start with the sockets. The sockets are actually based on the TCP/IP protocol. Now, if you consider the computers over the internet, of course there are various different protocols, but the most prominent one is a TCP/IP protocol. So every computer over the internet has its own IP number. IP stands for the Internet Protocol. So each computer has its designated IP number. When we try to connect to a different machine over the internet, say you want to connect from here to, let's say, Google, you get Google's IP number from another system named DNS. But once you have its IP number, you have the destination machine's IP number, you create packets and put the destination IP number in its header so that all the routers and the switches on the path know which way to send it. That's what we call routing is. That's what the routers do. But when the packet reaches the destination machine, like the server of Google, then on Google, to which process should it give that packet? Should it give it to the web server or the FTP server or the SSH server or any other server process? There are so many processes running on the same computer. So who gets this packet? This identification, finding the correct process to give, is done through what we call the ports. And the processes have the sockets that they connect to the ports. So the port is actually a holding place for the process, and the process creates, every process that wants to communicate creates a socket and attaches this socket to this port so that the other machine, when it specifies both the IP address of this machine, but when it comes to the machine, it also specifies to which port this packet should be delivered. And if there's a socket that is attached to this port, then the socket will take this packet and give it to the process to which that socket belongs. So the process will have received this. Now, there are actually 64K possible ports on a computer system. That's what the IP protocol allows. Each process, if they want to communicate over TCP/IP, they should be creating these sockets and setting up the connections. And to set up the connection, as I said, you should be first attaching the socket to this port. If you connect it to a TCP port, then you can use TCP/IP. If you connect it to a UDP port, you can use UDP/IP. Now, in the context of the discussion here, we'll just look at TCP. Okay, so for each socket, therefore, we have an associated IP number. Here, this IP number is just an example IP number, of course, it could be different, and an associated port. Typically, the IP number is a collection of 4 integers, less than 256, so from 0 to 255. We have 4 integers separated by 3 dots. So here, for example, the IP number is 161.25.19.8. So the part before the semicolon, before the colon is the IP number, and the part after the colon is the port number. So if a packet has this destination IP number and destination port number, the routers, without looking at the port number at all, they will just look at the IP number, destination IP number, and send it to the machine with this IP number, and only when it arrives at the destination IP number. Now, there's no means of looking at the IP number because we know we're at the correct computer. Now we look at the port number to identify to which process we should be giving it. So here the port number is 1625. So it will give it to this port number. And if there is an attached process, that process will get that packet. So this is how actually sockets programming basically works. So a connection, a communication link using sockets is actually composed of a pair of sockets. You connect this socket from this source process to this socket for the destination process. That's how 2 processes can communicate. Therefore, the communication link is actually defining the 2 ends of this connection by these sockets. The port numbers that are less than 1024, that means less than 1K, are said to be what we call the well-known ports. So that means these ports are internationally used for specific services. Like typically, for example, at port 80, we have the web services. At port 22, we have the SSH service, 21 for FTP service. So these are well-known port numbers. That means you will typically have SSH at 22, web at 80. That's why we call them well-known, so that anyone can easily find. In other words, for example, on your browser, when you type, say, www.cmp322.tr as the web address, by default, it will go to port 80 because it knows the web server should be there. If you want to put your web server at a different port address, port number, then everyone should know that port number, otherwise they will not be able to find your web server. That's why rather than using different port numbers, we typically prefer the well-known numbers. Similar is true for SSH and other services. Now, among the IP numbers, almost all of them, not all, but almost all of them, are public IP numbers. That means they are assigned by ICANN to different institutions, and they use it in their institutions. Now, there are some addresses that are called the private IP numbers, which should not be assigned to any public server on the internet. Those are used for not network address translation. Again, that's beyond the scope of this course. But there is one special address that you need to know, and that is 127.0.0.1, which is what we call the loopback address. This actually means this server. So for every server on the internet, if the destination address is 127.0.0.1, rather than trying to find a machine with that IP number, the IP protocol knows that it is the current server. So rather than sending it over the network, it just loops it back to the same server as if it came from the internet. That's why it's called a loopback service. This we typically use, for example, in the development phase. Uh, since if you don't have a destination machine at that moment during the development, we can have the server also running on our system, and as a destination IP, we will be using that. Later, at the time of deployment, we will be correcting actually the IP number rather than the loopback address. Now we will give the correct IP number and everything will just work magically. So, as I said, a connection is between two sockets. That means two different IP numbers and their port numbers. Note that the source and the destination port numbers need not be the same. Here, for example, for my browser could be working at this port number, which would be typically a random port number. The browser will pick any available port number. But for the destination, it should be sending it to the web server. And when it comes to the web server, we know that for the web services, the well-known port number is 80. So when it goes to this IP number, to this web server process, web server computer, it will go to the well-known web service, the HTTP daemon, which is typically working at 80. So the connection is defined between this IP number and port number versus this IP number and port number pair. How do you set up connections? The basic ideas are similar. Here we have the source code just for Java. C is slightly different, but the basic idea is you first create a socket, okay? Like we have defined a variable of type socket here, and for that socket, you have to call what's called the accept port number for the server process. So that will actually attach that socket to a specific port, and then in Java you create an output stream so that you can use for sending data. And this is the date server. The date server is actually a server to which you can just connect and learn the time and date. Okay, so if somebody connects, it will proceed and come to this line, and whatever the date is, it will convert that date to string and send it over this print writer variable defined as p out, which is actually attached, which is actually using this socket defined here. And when it sends the date, for the case of the date server, it's a very simple server. All it does is it sends the date. So it has already sent the date. So it closes the connection. It tears down the connection. So in this example, the connection is so short that you just connect, learn the date, and it's automatically turned down by using this close statement here. And for another connection, it will start all over again. Note that for the connections, we have two different types of connections. One is connection oriented, which is based on TCP, the Transport Control Protocol. TCP provides what we call the guaranteed service. That means if a packet is somehow lost on the network, which is, by the way, quite possible, the packet could be destructed during communications over the links, or a router or switch that's holding the packet could have just been down and the packet would be lost, or there could be other problems with routing and others. In such cases, TCP, even if it does not get a response, what we call an acknowledgement in time, it will retransmit the same packet. So in this way, it ensures that the packet, if there's a connection, the packet will arrive at the destination. In the case of UDP, there is no such check. Therefore, UDP is a much simpler protocol compared to TCP. But in the case of UDP, a packet might get lost. And if it gets lost, it's not a big deal. For example, when we're talking about, say, video communications, of course, you would like to transmit the packets to the other party when we are doing video streaming. But if a packet is lost, all that would happen is the image could be frozen just for a moment, but then the next packet will arrive, so it will continue. So rather than trying to send every video frame in a correct manner, it's more important in the case of video communications, for example, to get the packets transmitted in time, although we can tolerate some errors. But of course, this would work in video, but it would not work in, for example, in, say, bank transfers. You cannot afford an error in transmissions. Like if somebody is transferring funds and you lose the money in transfer, you will not be excused. So for such services, we do not use UDP in that case. So it really depends on what you want to do. There's also multicast, in which rather than a single IP number, in the case of a multicast, the multicast address corresponds to multiple computers. So you transmit and many computers receive it. So that's called multicasting. If everyone is receiving, then it's called broadcasting. So that's why TV communications is typically called broadcasting, because you send it to everyone who has a TV. Multicasting is more selected. Only the receivers who have joined that multicast group will be able to receive in the case of a multicast connection. Now, there is also the concept of remote procedure call. You know what a procedure call is? A procedure call is, or in other words, a function call, is there is a function. How do you make a function call? The function has a name. It has a list of parameters with their specific types, and you know where the function is, so the control jumps to the function. The parameters are passed to the function. The function takes those parameters as its specific arguments in that list, and using those arguments and its local variables, it does what it's supposed to do, and at the end it might be returning a value if it's not a void function, or if it's a void function, it's not returning anything, and that's it. Now, what if, remember, the function is actually part of that process. It's just a piece of, a subset of the instructions in that process. Now, what if I cut out this function from here on this process, and I carry it to another computer, say across the internet, and run that procedure or function over there? Now, you might say, why do I need this? Well, for some reasons you may need it. Examples. The function, for example, might require some specific hardware. For example, assume that you have to do some processing that requires, for example, very powerful GPU server. Okay, because you need to run that specific code, say some video processing, with tens of thousands of GPU, and you don't have such a GPU card on your computer, but there is a GPU server there. Okay, so you do what you want on your computer, just the rest of the stuff. But when it comes to that GPU processing, if you had the GPU card on your machine, you could run it on your computer. But since you don't have it, you just make a regular function call, but instead of executing a function here, it sends the request to that GPU server. The GPU server just executes the things related to that GPU service in that function. And when it is done, it sends the result back here. And for this process, it appears like it just made a local function call, but in fact, it was a remote function call. rather than function, we call these procedures. So instead of a local procedure call, now it becomes remote procedure call. Hence the name RPC, remote procedure call. Okay. Now, why would I do this? Because on this GPU server, this is an expensive server. So rather than specifically buying a new GPU server for every user, say in my institution, I could have a single powerful GPU server. So only for the GPU services, you make a function call and do the rest of the CPU dependent work on your computer. And now the GPU server might do similar service for another user, for another user, for another user. So this is more efficient. Now in such a case, when you're using RPC, to the regular program, to the rest of the program, you would like to leave minimal impact. Therefore, you would like to be able to, or you would like to enable that process to make a function call, not exactly same, but as much as possible similar to a regular function call. So instead of that, say, GPU function here, now you have what we call a stub, which is actually a substitute for the function that's to run here. So this is the real function running on the GPU server. Here you have a stub, a placeholder for this function. And what this placeholder does is you call that stub like your function, but that function cannot execute those instructions here. What it does is it takes your parameters, translate the parameters in a way that they can be transmitted to this GPU server here. So it will send those parameters. That's what we call marshalling the parameters. Actually, we're encapsulating the parameters, translating and encapsulating the parameters in a way that anyone can understand. So you take the parameters, convert them to something that could be transferred and understood across the internet. So we call that marshalling. Transfer the parameters in the marshalled manner. Here it will unmarshal them. Okay. And then after unmarshalling them, it will do the calculations, find the result. Now the result this time has to be, since it's going to be transferred over the network, the results now will be marshaled here, transferred to this side, unmarshaled by the stub, and finally the stub gives the result just like a regular return value to the caller. So from the point of view of the software here, it's as if like it called a local function, but magically it was a little bit slow because it had to go back and forth over the network. Of course, if the distance in time between these two servers is too high, it would not be good. So typically we would like to do it in a shorter distance or in a faster network. So these marshalling, unmarshalling are handled by what we call the stubs, both on the client side and the server side. So the data is therefore represented in a way that could be understood by any computer system. For example, my client here, say, could be an Intel machine, which uses what we call the little endian representation for integer values, whereas the GPU server here could be using, say, a Spark or Motorola processor, which would be using big endian. Now, what's the difference between little endian and big endian? You should remember this from earlier courses, but for those of you who forget it or who don't know it, big endian is the representation of numbers where the most significant bit is to the left. Just keep in mind, as in the case of big endian, it's very similar to the integers we're writing. Remember, the most significant digit is the leftmost one. So that's big endian. For the case of little endian, the bits are actually stored in the reverse order. So the most significant bit, rather than the left, it would be stored on the right. So Intel is using Little Endian, Spark, and Motorola, and many other processors, including the Java virtual machine. They're using the big endian representation. It's just how you represent it. But the important thing is it's different. It's just the other way around. So when I'm making a request from here to the server, I don't know what kind of a processor the server is using. That's not my machine. So what if they just changed the hardware there and now it's a different processor? So the endianness has just flipped. How could I know that on this side? Or some of my clients could be using Intel processors, and some others could be using, say, Spark processor. So while designing the server, am I going to design it according to this type of clients or this type of clients? Actually, I want to be able to handle all kinds of clients. So the solution is, no matter which endianness you're using, always send it according to big endian or little endian. Pick one. And what has been picked is big endian. So everybody converts to big endian and communicate over the network. We always talk in terms of big endian. If you were already using big endian, that means you wouldn't be changing anything. If not, then you would be changing it. This is true both for the server side and the client side. If we always talk using the same type of endianness, then there would be no problem. And that's what's being done in the RPC calls, and actually in all others. You also use it in the case of sockets, because again, in the case of sockets, the client and the server could be using different types of processors. Therefore, we prefer to switch to the network endianness. This is actually how the RPC system is working. So on the left column we have the client, and on the right column we have the server, and in the middle we have the messages that are being exchanged. So the client, for the client side, the user makes a kernel call, a system call to the kernel, because you want to make use of RPC. So you say you want to send RPC message to some procedure X, which is running on the server side. So the kernel creates a message and sends it to a matchmaker to find the port number. It's just saying, I want to call X, where the heck is X? Okay. So from the client to the server, you're sending it to what we call the well-known matchmaker port number, and saying, your question is actually, where is the remote procedure X? So the matchmaker receives this request and looks up its database, because if X has been earlier implemented, it would have been registered with the matchmaker. So it finds where it should be, and it replies to the client saying, what you're searching for, the remote procedure call X, is available at port P. So it sends this response to the client, and now the kernel will replace the port number with P rather than the matchmaker's port number, and send an RPC request to the server, this time using the port number P, and as the content, typically it would be sending these parameters in a marshalled manner. On the other side, on the server side, there would be a daemon listening to port P, otherwise you wouldn't get any response. So if a procedure has been registered for RPC on that server, there would be the daemon waiting for such requests, and says this is to port P. So it passes this message with the contents, with the marshalled contents, to the daemon process who is running this procedure X gives the Marshall parameters. These parameters will be unmarshalled, so in a way that procedure X would understand. Procedure X runs with these parameters, finds the results. The results are again marshalled, and then they're sent back to the client, to the caller process, to the correct port number. The kernel on the client machine will receive it and pass the result to the client process. So from the client's point of view, it was just a function call, and in response got the result, the return value. All the details of doing all this are handled by RPC system. They are implemented in the libraries. So from the client's point of view, it just made a function call and got the response. Well, it took some time to do it, but hopefully the time to do it would be, for example, in the case of a GPU, much faster than doing it without the GPU. Or if there was a special software that was required, say with some license, you could be using that license on that server easily over here. So these are different ways of using the RPC. There is yet another method of communication between the processes. Now this time the pipes are typically also used on the same computer system, as we will see why. So the pipe is actually working as a conduit, as a pipe mechanism between two processes that want to communicate. So the issues would be, is it unidirectional or bidirectional? If it's bidirectional, now do you mean half duplex or full duplex? The difference is, now bidirectional, as you know, means in both directions. In the case of half duplex, you either talk at one moment in time this way or this way, but not both at the same time. In the case of full duplex, you can talk in both directions at the same time. Okay, so that's the difference. Should there be always a relationship between the two processes, like the parent-child relationship, as we'll see, or can it be done without such a requirement? And we'll see that both answers are yes. We'll see soon. And can the pipes be used over the network? So we'll talk about two different types of pipes. One is called the ordinary pipes, and the other is called the named pipes. The ordinary pipes could be used between processes that are in parent-child relationship. Whereas in the case of named pipes, any two processes can communicate as long as, number one, they know the name. Number two, that you have the permission. Like if the server belongs to me, the client belongs to you, but you're not allowed to write to that pipe, then you cannot use it. But if I allow you to write to that pipe, and you know the name of the pipe, where it is, then you can directly use it. We don't need a parent-child relationship between your process and my process. In the case of ordinary pipes, as we will see now, that's a requirement. So let's start with the ordinary pipes. These are typically used for producer-consumer style systems where one is the parent of the other. So actually, what we have is, as you see in this figure, it's actually a pipe. So a pipe, as you know, has a volume. Just consider this as a regular type in which you have water. Okay? So when you put something in the pipe from this end, it will go towards the other end. So we talk about a right end from everybody's point of view. From the producer's point of view, say, I'm the producer, and next to me, assume there is the consumer process. So from my point of view, if I look at this pipe, say this is the pipe, from my point of view, this is the write end, okay, and this is the read end for the other one. So this way I will be communicating in one direction. So that's why actually the ordinary pipes are typically unidirectional. Well, what we do is we create the pipes in duplicates. So we have two pipes. So I use this pipe for sending, and there is yet another pipe, the black one, is used for receiving. So it's working the other way around. So I use the right end of this one and read end of this one actually. That's how things are working. So if you have two processes, sorry, let me do it this way. I have some producer process, or let me say parent process P1, okay, here. When it forks to create a child process, say P2, would be created here. Remember, when you create a child process, everything is duplicated, okay? Everything is duplicated except for what? The return value from fork is different so that the parent and the child know whether they're parent or a child. And their process IDs are different. Everything else is duplicated, including the file handles. If P1 had opened a file, P2 would also have that file already opened. If P1 is at a specific position in that file, P2 would also be at that position, right? So now P1 has created not a file, but it has created a pipe. So that pipe will be accessible also by the child process. Now, remember, this is the pipe between me and my child process. If we both try to write from the, and we have actually two pipes, if we try to write from the same end and read from the same end, it wouldn't work. If I'm using this end of it for writing, my child process should be using the other end for reading, so that what I write can be read by the child process, and vice versa if I need the reverse direction. Okay, so in Windows systems, Windows calls these anonymous pipes, but the idea you should keep in mind is we're creating actually pipes in typically tuples, in two tuples. So we will have two handles, 0 and 1, file descriptors 0. FD is just the name of the variable. You can just name it anything. But the parent, for example, will use 0 for writing, 1 for reading. If the parent is writing through 0, the child, since it knows it's a child process, it's not the parent process, the child should use 0 for reading, 1 for writing, just the other way around. Okay, so it's just like when you want to read, for example, in the case of parent process, you would be, for example, reading FD1 for the parent process. In a child process, you would just be doing the other way around. You would be reading from FD0. And just the inverse for write. In the parent process, you would be writing to 0. And for the child process, you would be writing to, this time, 1. Okay, so that one writes and the other one reads. Okay, but note that in this case it would be one writer and one reader. But this is typically how the ordinary pipes are working. But pay attention, once again, this would work if and only if the two processes have the parent-child relationship, because that is actually how the child process inherits the parent's file descriptors for the pipe. Otherwise, the child process cannot know the parent's pipe file descriptors, and also it requires that the the ordinary pipe, is created before fork, because that's how you inherit it. Anything done after fork by the parent, of course, is not inherited by the child process. So the other type of pipe is the named pipe. In the case of named pipes, as the name implies, the pipe itself has a name. Okay, therefore, you know how to refer to that, and as a result of this, you don't need parent-child relationship. A named pipe is just like a regular pipe. Actually, it looks very similar to a regular pipe. So it's a file actually in the file system, but the difference is that actually a named pipe is a FIFO system, first in, first out system. What does that mean? It's just like a regular file, except for that, remember, in the case of a file, you can read from anywhere you want, and you can, go back and read once again the same stuff. That's not possible in the named pipes. In the named pipes, one of the processes, again, we don't require parent-child relationship here. A process creates a pipe with a specific name. As long as the other process knows the place and name of the pipe, and also read-write permissions to that pipe, it can access the same pipe. Now, the pipe is empty. Say in process P2, you say read, the pipe is empty, and if it's a blocking read, P2 just gets blocked there. When P1 writes to this pipe, since P2 was blocked for reading it, it will just immediately take that value. And when you read the value, the interesting thing about the pipe is it disappears from the pipe because P2 has taken it. Now, it is possible that there was also another P3 that was also blocked or trying to read from the pipe. One of them gets the value and the other one still remains there. So you could write, so what I'm saying is, it would be like P1 writes here, both P2 and P3 want to read from here. What P1 writes, just due to how the system selected, could have been passed to P2. Then P3 will not get anything. Now P2 has already got what it wants, so it will not be trying to read, hopefully, for something. P1 writes once again. Now P3 will get that. Now, assume the following scenario. P1 writes, let's say, A. Then it writes B, so B goes behind A. C goes behind B. Now P2 comes and wants to read something. It will get A, so P2 gets A. So the value A will be removed from here. Therefore, B is shifted here. So here we get C, and C is removed. Okay, that's why it works like a pipe. Now, another process, P3, wants to read something. So P3 will get the value B. Therefore, B will be removed here. C comes here. and that's the pipe. Another process, or maybe one of the previous processes, doesn't matter, once you get something and gets C, and another one once you get something and will get blocked. P5 gets blocked because there's nothing in the pipe. Now, some process P1, or let's say this time P6, say puts the value X, it will come here, P5 was already waiting for it, and it will immediately disappear from here, and P5 will get X. This works as long as we know the name of this pipe here. So we don't require any any parent-child relationship here, but the use of the use of ordinary pipes is simple. So if we already have a parent-child relationship, we typically prefer to use unnamed pipes. But if we need, if you don't want a parent-child relationship, then the named pipes are a good tool to use. So, sorry, I couldn't get the focus on this slide. So that would be the end of this chapter. So please go over sections 1, 2, 3, and 4 as the reading assignments.